We have self-driving cars and pocket supercomputers. But in healthcare, we are still using trial and error. We give a patient a drug and wait to see if it works. We perform surgery and hope the anatomy is what we expect. We practice medicine on the actual patient. But what if you didn't have to? In 1970, an oxygen tank exploded on Apollo 13, 200,000 miles from Earth. The crew was losing air, the temperature was dropping, and the engineers in Houston had a problem. They needed to write a new procedure to fix the ship. But they couldn't guess. They couldn't use trial and error, because in space, trial and error meant death. So they didn't test the solution on the astronauts. They tested it on a twin, a precise physical replica of the ship that stayed on the ground. They pushed the twin to its breaking point. They broke the twin so the real crew could survive. Now this idea is being revived in medicine, the idea of the digital twin, a perfect in silico replica of your biology, a digital stunt double that can take the chemotherapy, face the surgery, and test the experimental drug, so you don't have to. This isn't science fiction. It is a technology borrowed from rocket science, and it is already saving lives at Boston Children's Hospital. Today, we are going to look at the discovery that is about to turn medicine from a guessing game into an exact science. If you work in a hospital today, you know the dirty secret of modern medicine. We are still guessing. We call it evidence-based practice, and it sounds scientific. But in reality, it is a game of averages. When a patient comes in with heart failure, we look at the clinical guidelines. Those guidelines are based on trials done on tens of thousands of people. We look at the average response to a drug. We look at the average risk of a surgery. But your patient is not an average. Your patient is a specific biological puzzle that has never existed before. And applying average data to a unique human is where the mistakes happen. Something that every nurse sees: Russian roulette with medications. For example, a patient comes in with hypertension. They are started on a medication and it is adjusted as needed. But then they have side effects, so the patient is switched to another medication. This cycle of trial and error can take months to find a medication that works for that patient. Meanwhile, the patient is suffering and the provider is frustrated. This patient-specific problem is being solved with a generic manual. This approach terrified an engineer named Steve Levine. Levine wasn't a doctor. He was a crash test expert at a massive tech company called Dassault Systems. His entire job was building digital cars and smashing them into digital walls. He never built a physical car until he had destroyed 1,000 digital ones first. But then, his daughter Jessie was born. Jessie had a rare congenital heart defect called corrected transposition of the great arteries. Her heart's ventricles were reversed and the arteries twisted. The doctors told Levine they could fix it, but they also told him the truth. They wouldn't know exactly what they were dealing with until they operated. They had to improvise. They had to use trial and error on his daughter's living, beating heart. Levine looked at his work, where he could simulate a crash test with 99% accuracy. Then he looked at the operating room, and he asked the obvious question: why do we have better data for a Toyota Camry than we do for a human child? That anger launched the Living Heart Project. The goal was simple: stop treating the body like a mystery and start treating it like a machine that you can test, break, and fix in a digital environment long before you ever touch the patient. So, how do you actually copy and paste a human being into a computer? It starts with a concept called in silico. You may have heard of in vivo, which means testing in the body, in vitro, which means testing in a test tube. Then there's in silico, which means in silicon. It means testing inside the microchips of a computer. But this is not just a 3D animation like you would see in a Pixar movie. A digital twin follows the laws of physics, and to build one, engineers need data, massive amounts of it. It starts with the data source layer. We take the patient's MRI and CT scans, but we don't just look at the pictures. We use AI to perform image segmentation. The computer traces the exact geometry of the organs, creating a 3D map that is accurate down to the millimeter. Then we add the physics. Engineers use two massive mathematical engines to bring this map to life. The first engine is called computational fluid dynamics. Engineers use this to model how fuel flows through a rocket engine, but in healthcare, it models blood. It solves complex physics equations thousands of times per second, calculating the speed and pressure of every single drop of blood in your arteries. It can even predict a blood clot forming in a virtual vessel just by doing the math. The second engine is called finite element analysis. Imagine taking a human heart and slicing it into thousands of tiny, microscopic cubes. We tell the computer exactly how stiff or stretchy each cube is. We tell it how electricity moves through that specific cube. Then, when you connect all these digital building blocks, you don't just get a shape, you get a structure that reacts. When you turn the power on, the digital heart beats. It contracts. It reacts to pressure exactly like real tissue. It isn't just a picture of a heart, it is a heart, translated into code. This changes the game for surgeons. It means they can put on a VR headset and literally step inside your anatomy. They can practice a cut. They can deploy a stent. If they make a mistake in the simulation, the virtual heart fails. But in the real world, they just hit reset and they try again until the procedure is perfect. So, what does this look like during a typical hospital shift? For the frontline healthcare worker, medicine is often a battle against the unknown. You have the charts, the scans, but until you are in the room, until you make the incision, you never know exactly what you're going to find. That uncertainty is the source of massive burnout. It is the stress of constantly asking, what if I miss something? This is where a digital twin changes the job. It happened at Boston Children's Hospital with the Seed family. 3 days after she was born, Annika Seed was diagnosed with a rare combination of defects called tetralogy of Fallot with pulmonary atresia. Essentially, the valve that lets blood flow from the right ventricle to the lungs was completely missing. This starved Annika's body of oxygen and required a series of risky, open-heart surgeries just to keep her alive. In the past, the surgical team would have relied on 2D scans. They would have stared at black and white X-rays and tried to mentally imagine the 3D structure of Annika's tiny, complex heart. They would have had to build the plan inside their heads. But Dr. David Hoganson did something different. He ordered a digital twin of Annika's heart. Using MRI data, they built a precise 3D replica of her specific anatomy. They didn't just look at it, they operated on it. Dr. Hoganson was able to test different surgical patches on the digital heart first. He could see exactly how the blood would flow after the surgery. He realized that his standard plan wasn't the best one for Annika. The simulation showed that a specific type of patch would work better for her unique anatomy. For the surgical team, this eliminated the hardest part of the job. They walked into the operating room knowing the anatomy perfectly. They knew exactly which patch to grab before they even scrubbed in. It turned a high-pressure scramble into a choreographed routine, and it changed the conversation with the family. Allison Seed, Annika's mother, said that seeing the digital twin gave them ownership of Annika's care. It wasn't a mystery anymore. They weren't just handing Annika over to luck, they were handing her over to a plan that had already been proven to work. But the digital twin isn't just for high-stakes surgery. It is also for the silent killer that overwhelms our healthcare system every day: chronic disease. If you are a nurse, you know the struggle of managing type 2 diabetes. You educate the patient, you prescribe the insulin, you talk about diet, but 6 months later, they are back in the ER with high blood sugar. Why? Because metabolism is unique. A slice of pizza might spike a person's blood sugar to 200, but it might only spike yours to 120. We've been treating diabetes with a one-size-fits-all approach, but now companies like Twin Health are building metabolic twins. This is a digital copy of a patient's entire metabolism. It is fed by thousands of data points from continuous glucose monitors, smartwatches, and sleep trackers. It creates a dynamic model of how that specific patient processes energy. Instead of a doctor saying, "Eat less carbs," the digital twin says, "Hey, for your specific biology, if you eat oatmeal at 8 a.m., you'll crash. But if you eat eggs, you won't." It predicts the spike before it happens. And the results for the healthcare team are shocking. In clinical studies, patients using these metabolic twins saw a 71% reduction in insulin use. For the primary care provider or the diabetic nurse educator, this is a revolution. It changes the conversation from compliance to precision. You aren't nagging the patient to follow a generic rule. You are giving them a personalized map of their own body. You are showing them exactly what works for them. This moves healthcare from the hospital to the home, and it prevents an emergency before it can happen.
If you've ever been inside a hospital, you've probably heard this sound, or this beep, or this one. Then imagine hearing it all at the same time.
This technology doesn't just change the patient, it changes the ward itself. If you work on an inpatient unit, your shift has a soundtrack. It is the sound of beeping, commonly referred to as alarm fatigue. You're constantly bombarded by thousands of alerts per shift, and the reality is staggering. Research indicates that 72 to 99% of these clinical alarms are false or clinically insignificant. A patient rolls over, a sensor comes loose, a wire gets tugged, but you still have to check every single one. You spend your day running from room to room, reacting to noise, constantly wondering which alarm is the real one. This is where the digital twin becomes the ultimate filter, because the system understands the physics of that specific patient. It's context aware, and it knows the difference between a heart stopping and a wire disconnecting. It can look at the data trends and say, this isn't an emergency, this is just movement. It suppresses the noise. It creates what engineers call the quiet hospital. Instead of reacting to a crash, the system predicts it. It creates a pre-alert. It tells the nurse, based on current trends, this patient's blood pressure will likely drop in 2 hours. It shifts your role from reacting to crises to preventing them. It gives you time to intervene before the emergency happens. And it goes even further. Hospitals are now building operational twins of the entire building. Imagine a command center dashboard that mimics the entire hospital floor. It predicts patient flow. It tells the charge nurse, you're going to be short-staffed in the ICU in 4 hours because of 3 incoming traumas. It allows the team to adjust staffing before the chaos starts. And the impact on the workload is massive. Early studies suggest that AI-integrated documentation and monitoring tools like this could save providers up to 2 hours of administrative work per day. That's 2 hours you aren't staring at a screen. That's 2 hours you aren't chasing false alarms. That's 2 hours you can spend actually looking at your patient. However amazing the digital twin is, it cannot do everything. While computer code can calculate blood flow, it cannot hold a hand. It cannot comfort a terrified family member. It cannot notice the subtle look of pain in a patient's eyes that a sensor might miss. What the digital twin does do is strip away the grunt work. It strips away the calculation and the stress of guessing. It stops the noise. It allows the healthcare worker to stop staring at monitors and start looking at the patient. We're moving toward a future where we make our mistakes on code so we don't have to make them on people. And for the frontline healthcare worker, that means a shift from managing patients to actually healing them.